I'm taking a great risk here. And potentially getting a copyright strike in this lecture pausing before it even gets started. Maybe if I talk over it now and then, YouTube won't notice that I'm using someone else's material. Maybe there's not enough audio, so it'll be okay. Let me resize the window. So they don't notice. Wait for it, it's the cool bit. This bit, yes! Alright, I'm gonna stop it there. Because I didn't get a copyright strike. that's a good thing. Good afternoon, everyone. I thought it'd be funny today because, oh shit. Warning, we've detected copyright audio and video. Your stream may be temporarily blocked. We'll see. I've stopped now, so hopefully the stream doesn't get blocked. Andrew's saying if YouTube can pick out flipped and pitch shifted video, then they can pick out this. So yes, they did detect it, but the lecture has not stopped, which is good. I knew I'd only have a very short amount of time. You may find if you play this back later that the first couple of minutes of this lecture will get cut out. But I mean, like, yeah, I could get demonetized and that's fine because there's nothing on my YouTube channel that's monetized, so it's okay. I was doing some personal streams at some point in the channel, and I monetized like one of them for a few days, and I just went, oh, I can't be bothered. You know, it's not really that important. I'm interacting with students, so I will take my pay from UNSW as my pay instead of trying to make money off YouTube. So, some of you may have recognized, what's the year, 1998's Matrix? I thought that was a funny joke. Last week, when we were working with mathematical matrices, I made the joke of Transformers because we're doing transform matrices, and so this week I'm going into the Matrix jokes. Matrix, however, quite a significant film. I have some stuff in the break time slide. I'm going to talk about it later, so I'll give you some more juice about the Matrix. Anyone who figures out the link. There's a link to my t-shirt today to do with the Matrix. I know there is one person who actually works at this particular company that I'm wearing the t-shirt of, who will recognize this, because this is actually the staff t-shirt. I used to have my ways of getting things like that. I don't anymore. I don't have a link to the staff anymore. But I'll talk about that in the break. But let's talk about what we're going to talk about in the lecture today. I did a bit of a psych there where I had the thumbnail for this lecture as Quake, and I was going to go into 3D graphics, and I'm expecting everyone thought I was going to start playing Quake, but it did a switcheroo on you, so I'm not always predictable on what I'm going to do. Okay, so let's go over quickly what we did last week. Last week we looked at the OpenGL pipeline, so we looked at the idea of how all of our bits and pieces of the details of our vertices and the vertex attributes and stuff are actually handled by the vertex buffer object, the vertex array object, and things like that, and how we can put all these things together to go from the theoretical idea of objects through to rasterizing them into actually visible pixels in the same way they're going to be seen on screen, filling those pixels in with color using fragment shaders, and then having them eventually appear. That's a subset of the entire pipeline. We're always going to be talking about more about that as we go along. We talked about textures. So we talked about taking something like a 2D image. Textures can also be things like 3D. You can have 1D textures as well, but I mean, like, I say the 1D ones are less useful. The 3D ones can be amazing, but cumbersome because they take up, 1,000 times, roughly, however many pixels there are, but an order of magnitude more memory in your graphics card than a 2D texture will. So yeah, you gotta make a really kind of strong justification for using a 3D texture if you want to use it. We also talked about transforms, and so we talked about the idea that we can have our points, our vertices, which make up an object, and we can do things like rotate them, scale them, or translate them, moving them around. So that led us to the possibility of how a 2D game could be made. And so we were looking at, say, doing things like putting images like sprites on rectangles and moving those rectangles around, and how if you wanted to, you could make like a Mario-like game just with that capability. So all you need is the ability to do textures on rectangles and transforms, and then you've got it. Like, there's a few little details there. You need to have a real-time loop and stuff like that. Your tutors have looked at some of that stuff already. The ability to have a loop that's constantly updating, and every time it updates, it figures out how much time has passed since the last time it rendered an image to screen, how far things should have moved in that time, and things like that. Also doing things like detecting input in between each frame and things like that. So those are the kinds of things that we'll get into a little bit, but not a huge amount, because that's a sort of like a game development thing that's not necessarily a graphics thing, and we're focused on the graphics in this course. Because there's a whole bunch of stuff, like we could talk about physics and collision detection and stuff like that. Controllers designed for humans, head-up displays, all these kinds of things, super important for games, not necessarily for graphics. We're going to be focusing on the graphics side of things. But I know that a lot of people are interested in making games, so I'm just going to like keep everything closely to the context of games. But I mean, I'm also happy to say that, like, you know, every now and then I'm going to show bits of movies. I figured out how much I can show now. If I keep it under about 60 seconds, the copyright strike fades away pretty quickly. And I can go on to talk about things. What I may do sometimes is, instead of showing the actual video, I'll just talk about it and say, okay, go off and watch this one. It's interesting. So today's will be The Matrix. I actually forgot to put a slide in about the reading list. You know, I was going to put reading lists of things. I should have put that in today. I even have a slide talking about The Matrix, but it's not, I didn't officially call it reading list stuff. So what are we going to do today? Today, we are expanding our horizons. Literally. Sorry. Laughing at my own jokes. We are entering the third dimension. So, up until this point, I like it because week 2 we did 2D, and then week 3 we do 3D. So it's like, it's this funny little numerical advancement of things. So we're going to look at what changes when we go between 2D graphics and 3D graphics. So we're going to talk about what we've taught you so far with 2D and what we're going to need in 3D and how we're going to make the jump from one to the other. Yes, Michael says here, week 10, 10D. Yes, by the time we get to... Actually, we should do some real-time programming in week 4, so we're programming in time as well. I don't know if we're necessarily going to do that. I could throw it in just for a meme, but, like, you know, we are still doing a course here where you want to learn things, and we're definitely not going to 5 dimensions. Although I should point out that, yes, 5-dimensional thinking does come into graphics when you get into certain things like inverse kinematics and stuff like that. I never fully understood it myself, so I would have trouble teaching it. But anyway, let's stick to 3D at the moment, because 3D is something that is generally understood by humans because we exist in a 3-dimensional world, right? So it's easy for us to comprehend the third dimension. The weird thing about our computer graphics is that the majority of the time we're going to be doing this on a 2-dimensional screen. So what we're doing is we're viewing a projection of a 3-dimensional space. But the virtual world that we're creating in graphics to be able to work with and stuff, move around and have objects in, is going to be a 3-dimensional virtual world, which we're then going to be viewing in a 2-dimensional way. Obviously, this changes entirely when you're working in VR, where you are viewing things with sort of slightly more genuine depth perception when we're working with, like, stereoscopic depth perception. We're not going to be covering that in huge detail in this course. I'm just going to mention it every now and then because it's not that different. Like, usually when we go from a 3D game to a VR game or something like that, or a VR experience or anything like that, we don't really change our assets or anything. The only thing that changes is certain parts of the render pipeline that renders from 2 perspectives at the same time. I could talk at length about that. I've actually worked in that kind of stuff, but we're not going to go into detail in this course. I think we've got the basics to cover instead. So we're going to look at 3D objects, just a little thing covering what 3D objects are and how they work. And we're going to talk about coordinate spaces and transforms and things. So we're going to continue learning about these transform matrices. So up till now, we've learned that transform matrices are a way to basically move objects around in our scene. So an object being a set of vertices. The set of vertices connected together in a particular way as triangles, and this depends on your setup, right? You have your index buffer and stuff like that to define the object. And if we apply a matrix to all the points in the object, the whole object moves somewhere. But we're going to expand that thinking a little bit further as we go deeper into the matrix. See, this whole thing wouldn't have worked if I hadn't shown that video at the beginning. It was worth risking the copyright strike. And then we're going to do our first thing that is a very fundamentally different thing between 2D and 3D, is the idea of a camera being in the scene. So the idea, if you've got a three-dimensional scene, you have a camera that exists inside the scene and it can move around inside the scene, which means it has its own kind of existence in three-dimensional space. We're going to look at building one of them up. Today, we are not going to get time to get into how it actually sees anything. So we're going to think about it as an object that can exist, it can move around and stuff. And then on Wednesday, we'll look at how it actually views the world and some other things that build up from what we have here. So let's look at the kind of crossover point between 2D and 3D. So what I've taught you so far about two-dimensional graphics, how do we apply that to three-dimensional graphics, or what kind of things that we've learned in 2D we can apply in 3D. Current capabilities that we've built up so far. Simple stuff for now. Later on, you'll be like, oh, we can do more than this, which is cool. But we have shapes made up of triangles. So vertices joined together into shapes, makes them triangles, and we can put textures on those triangles. So not just on those triangles, we can put a texture across an entire object. So a lot of people at the moment will have done textures on rectangles, but we can expand this further beyond textures on rectangles into textures across larger surfaces. If anyone's done like a circle yet or something, it's going to be multiple triangles. We've also got transforms allowing us to move things around, to place things at particular positions in our space, to reshape things to different sizes and stuff like that. So that's our current capability in 2D graphics. So in 3D graphics, what are we going to do? So what are we doing in 3D? In 3D, we're going to have shapes made of rectangles. We're going to have textures on those objects, and we are going to have transforms to put those objects somewhere in our space. So that's why I picked this meme, because it made me laugh. I didn't actually put an image credit on this meme because it's from The Office, if you said it, but I don't even know who to credit for a meme. It's like the person that made the meme out of the source material, or the people that the source material is from. But anyway, you may have seen this before. So strangely enough, the way that we were teaching this subject was with the long-term intention that you would get to 3D. Hexa says I should just credit myself because I put 2D and 3D into the meme. So in 3 dimensions, we have shapes that are made up of triangles. So vertices and triangles are still the building blocks of our 3D objects in our polygon rendering. We're going to wrap textures on objects in exactly the same way that we're doing in 2 dimensions. It's just when it gets into 3 dimensions, it actually moves around a surface rather than just being flat on a surface. And our transforms are very, very similar. I'm going to go into the detail and the differences between these things, but we're still going to be using exactly the same process of using transforms to move things, or using transforms to reshape things. I'm trying to use other words for the word transform, basically. So our matrices that we're going to transform things are very, very similar. So what we're getting here is that, like, you know, there's nothing that we've taught you that you're leaving behind when you go from 2D to 3D. So this is the deal. We've been teaching you 3D graphics all along. The only thing we've been doing is just for the first 2 weeks, we've been intentionally not using the Z-axis for anything. So we think about a set of axes. From your viewpoint, I think from your viewpoint this is correct. I'm just looking at my other screen to see. So we've got an x-axis, which is my thumb, which goes from the left to the right, in a sense. Well, it goes positively to the right, negatively to the left. It's really extending in both directions. A y-axis that goes up and down, and the z-axis comes out of the screen towards you. So that has been our third dimension for what we've done so far, but we've never used the z-axis. Have you noticed that a lot of things had 3 coordinates, but the z was 0 for everything? So everything was at a particular distance from the camera, and we were just treating that as like a flat kind of canvas that everything was on. But if we start to use the z coordinates, we can start doing interesting things with it. So if we use the z, that means that we can place things in front of each other, place things further towards or away from our viewpoint. We are going to get more fiddly when we get our viewpoint though. But when we're using triangles for objects, a triangle is a 2-dimensional object. So this is something that's important to note, that if you take any 3 points, they will, so long as they're not, like all 3 of them aren't collinear, in a sense, they're not all along one line, those 3 points will be a plane in existence somewhere. So 3 points anywhere, so long as they're not collinear, because then they're in one dimension if they're all in the same line, they will always map out a 2-dimensional space. But if we have multiple triangles, each one being a different plane, then we can make, you know, this kind of shaped surface. Like, I'm calling it shaped, not curved, because the surface itself is not necessarily curved, but you can give the illusion of curved surfaces by having lots of triangles that are slowly kind of changing angle as they connect to each other. And so that way we can build up these three-dimensional objects out of 2-dimensional surfaces. So every single surface is a flat, dead flat triangle, like triangles can't bend, and we put multiple of them together, and then they can make something that appears like a curved surface. When we're working with textures, and the way they work with vertices, they work exactly the same way as they work in 2 dimensions. So when we were doing things like plastering an image on a rectangle, we had texture coordinates on like the corners, and in between those corners, in between the verts, the fragment shader was going to interpolate across the texture, pick up texels, color from the texels in the texture, and place them on the object. When we do this with 3D objects, exactly the same thing happens as with our 2D rectangles. The only thing that might be interesting about it is we see textures that wrap entirely around an object. So part of the texture is on one side of the object, and then it wraps all the way around, and then the texture sort of meets its other end on the other side. I even showed examples of that when I showed that the Quake grunt or enforcer, I can't remember, like one of the soldiers from Quake, and showing the texture and showing the model, and you can kind of see how the texture was being wrapped around the model. So we're not actually going to need much more thinking about textures than what we've already learnt in order to use them in 3D. The things that are going to change a little bit though is some of our transforms are going to get a little bit weirder in that they're going to add a 3rd dimension. Some of them are easy when they go into the third dimension. Some of them get a little bit more fiddly. I'm going to go into detail on the transforms themselves. Most of this other stuff we don't even need to think that much for about adding. Okay, so transforms. If our transform matrices are adding a dimension, that means they're now going to be 4x4 matrices. So last week, I don't have the slides up here, it doesn't matter. You can go back and look over the slides if you want. Last week I showed 3-dimensional matrices that were working on 2-dimensional points. So the 2-dimensional point still had a W on the end. That is the homogeneous coordinate that we use that helps these matrices multiply things out more easily. For the moment, W is always 1. And that's going to allow us to do certain multiplications with our transforms. But now we're going to have an X and a Y and a Z. So from here on out, all of our matrices are going to be 4x4 matrices. So even if we were doing 2D, we could use 4x4 matrices, because all we do is just ignore the Z coordinate in these matrices. Scale is an easy kind of expansion into 3D. Like, we can take this scale X and scale Y here. And when this expands into 3D, it's just scale X, scale Y, and scale Z. So when we want to scale things in all 3 dimensions, the sort of format and layout of the transform is the same. It was on this kind of diagonal layout as it was, and so we're just continuing this pattern. The scale transform works very similarly to the way that we expect it to work. It's just going to sort of multiply your distance away from the origin by whatever factors are in these 3 positions. So I don't think I need to talk too much about that. Translate also is a very, very easy one, where it just says, this is how much movement we have along the x coordinate. This is how much movement we have along the y coordinate. We've now added this z coordinate. So translating in z is just an extra number in the 4x4 matrix. And you'll recognize the diagonal ones is the identity matrix that this is based on. And the diagonal ones means a lot of things are unchanged. So we're not scaling in the x, the y, or the z, but we're moving everything by these certain amounts in x, y, z. So scale and translate, pretty easy to think about going from 2D to 3D. Probably didn't even need to cover this that much. I could have just said, okay, this goes to this. I don't even need to talk about it. But rotate gets a little bit fiddly. So depending on how in tune you are with matrix multiplication, how often you've done it, you'll know that matrices work on this rows and columns thing. So this row will be multiplied by a column, this row will be multiplied by another column, and things like that. So if you know that, you will see how this kind of setup works. So when we're rotating in 3D, we're going to be rotating around a vector. So the simplest way we're going to do this, and we're going to usually be doing all of our rotations based on the axes of the world. So the axes of the world are the X, Y, and Z axes. So your rotation that I showed you previously was not just a 2-dimensional rotation. It was actually a rotation around the Z axis. So the Z axis, if it is pointing towards you, is like a pole that extends out the front of our monitor. And we can rotate anything around that as if it was like, you know, like a physical pin in an object that you can then rotate around. When we go into 3D, this setup remains like the cos negative sine and the sine and cos in the top left corner. And this thing is still doing a rotation around the z-axis, and it's actually pretty much exactly the same transform as it was in the 2D, but now it's explicitly saying that it is not changing the z-axis. So if you were to look at the way this thing multiplies out, the layout of the zeros and the ones in the 3rd column and the 3rd row will make sure that the z-axis of anything that we're rotating is unaffected by the transform, and it also stops the z coordinate from changing the x's or the y coordinates on things. So this rotation matrix, which is rotating around the z-axis, is only capable of affecting the x and y coordinates. So if I have something here and I have my z-axis kind of going through, it's actually going to be coming out towards you. I do like the fact that I can just like point at my camera like that. That's the z-axis. It's poking you in the eye. The rotation around it like this object is flat. It is not moving forwards or backwards, or even if it is a 3D object, none of the points are going to move forwards or backwards. They're not going to move along the z-axis. They're only going to rotate around it. So this is the first rotation matrix, and the one that matches up very closely with what we've done before because we used it. You can already guess a little bit about how we might do rotation around the other axes. Is we're going to use this similar kind of setup, pieces of the identity matrix to dodge certain other axes. So if I want to rotate around the x-axis, what I do is I say in the first column and the first row, here it's not really the 4th ones, but like these 3 numbers here and these 3 numbers here are going to make sure that the x-axis is not affected in this rotation, and then the y-axis and the x coordinate is not going to be affected, but the y coordinate and the z coordinate of whatever we're rotating is going to change. So this is our x-axis, so this is something that can tip forwards or backwards like this. And around the y-axis is something that's going to rotate like that. And the same kind of thing where the second coordinate is the y coordinate, and that's the one that's being avoided by the sines and the coses. The sines and the coses is just a is that a Pythagorean trigonometrical? I don't know which category it is, but you know, circle geometry, basic circle geometry that cos and sine, as you go along, they go up in a wave. If you combine them for the two different coordinates, it's just going to draw a circle. So that's why the rotation matrices have the sine and cos in it, because they're just moving coordinates around a circle. So when we do rotations, we will most often be doing things like combining rotations in two different axes at once or something like that. We're not necessarily going to go too deep into finding a particular vector and then rotating around that particular vector, or it's often easier to just tilt something to a certain angle and then rotate it on a particular angle if you're trying to get a really particular twist going on. A lot of the time as well with our rotations, we're going to be, in a sense, asking our computer to figure out what these rotations are going to be for us. So we are going to be doing a little bit of that at some point with camera controls and things like that. So we're going to be rotating the camera's matrix. Bob's asking if zoom in and zoom out is just modifying the z-axis. To a certain extent, yes. It's you could zoom in and out by translating objects closer or further from the camera. But in order to understand how to do that, I'm first going to have to show you how the camera works, and then I'm going to have to show you how we actually do what's known as a perspective projection. So, you know, we look in the world and we can, like, we're looking at the world like in straight lines and stuff like that. So what we've seen so far in our graphics is everything is just placed, you know, and if you move it further, closer or further away from you, it doesn't change in size. But there are ways that we're going to do that. I'm going to cover that on Wednesday. And once we've got that, then you will be able to do stuff like zooming by moving things closer and further away without changing their size. If you want to sort of approximate that at the moment, you can actually just scale things. But it won't really be taking into account things maybe moving through each other and stuff like that. So there's more to learn before we can actually really learn about what zoom is, in a sense. And plenty of games are going to fudge that in interesting ways as well. So sometimes, I think one of the biggest things that you're going to see in a lot of like first-person shooter games is like soldiers running around with their gun, and then they bring their gun up, and there's this thing called aim down sights, which is where they look through like a zoom scope or something, and it changes their field of view. Sometimes that's a camera moving in a scene, or sometimes it's actually switching between two different viewpoints. But I think I need to teach you more about how these things work before we get into those details. But we will get there. Trust me, we will get there. Okay, so those are like rotations. So now we have a scale, translate, and a rotate in 3 dimensions, which means that's all we need to do to be able to take our transforms to 3 dimensions. As I said, you know, the jump from 2D to 3D is not a huge amount of effort. I guess just remembering that these transforms are slightly different from each other. Having said that, we will only rarely be manually putting together transforms. You know, we will rarely be manually putting together rotator in X, Y, or Z. GLM has the capability to build rotation matrices for us. You don't have to memorize where the cos and negative sine are and stuff like that. But it is interesting if you want to look at it, the trigonometry of a circle and how the cos and sine work and their relationship to right-angled triangles and all this kind of stuff. It is a fun thing to look up, but we're not going to go into super detail in the course. Okay, so moving on, I want to talk a little bit about three-dimensional objects and how they work. So back to the teapot, good old teapot. I should get one of those teapots made into a glass so I can drink out of like a clear version of that teapot while I'm lecturing. So in your tutorials, in the stuff you've been working on, you've already made rectangles. So you've made an object that's made up of multiple triangles. And that's nice and important, because if you can make an object made up of two triangles, it means you can then extrapolate that to make an object made out of, I don't know how many triangles are in here, but several hundred minimum. Let's say, I'm just going to call it 1,000 so I don't have to think about it too much. Let's say that this teapot was made out of 1,000 triangles. They haven't even made the triangles in most of these. These are just the rectangles, but we know that if we're going to have rectangles, we're going to be splitting all of these rectangles up into pairs of triangles, because that way we can guarantee everything's a flat plane. A rectangle you can't guarantee as a flat plane. You can make a rectangle so that it's weirdly warped, and then it's hard to tell exactly where it sits. Triangles, you always know that any point inside a triangle is a linear interpolation of the distance between the 3 points. So it's always linearly a balance between, it's like an average of the 3 points. And that makes it really, really easy to work with mathematically. Rectangles, less so. It's still possible, but it's much easier to break them up into triangles. So, the 3D triangles then, well, they're all two-dimensional, but they're all in a three-dimensional space, are then forming the outer surface of the object. So, we get this interesting thing that Dongs said, how will you drink out of it? It has no bottom. Yes, okay. The running joke is that no one ever put any verts on the bottom of the teapot, which we would if we were going to actually make this, especially if you're going to pour it and you're going to see the bottom. Anyway, the vertices can actually form surfaces that wrap entirely around an object. So we can have verts going in like a ring, in a sense. That means that the chain of triangles are going to link back up to where they started. So our index buffer is going to be able to say, all right, we go from vertex 0 all the way through to like vertex 100 or whatever it's going to be. And then that final triangle actually links back up to vertex 0. And then if we've got it like that, it means our object is complete and sealed, in a sense. Like, we have not left any gaps in our object that you could potentially see through or render vision through by accident or something like that. And then our triangles form the idea of the outer surface of the object. So you may have heard of things like skins in computer games and graphics and stuff like that. It's very much that idea that the 3D objects that we have made from a graphical perspective are nearly not objects. They're only the outer visible surface of objects. So the only things that we're worried about in graphics is the outer visible surface of the objects. This does change a little bit when we get into animating objects. We're going to talk about that a little bit. I don't know how much depth to go into in that, because it's sort of a side topic, but it is something that's quite interesting to think about. So when we start animating things, we start to think that maybe they have some kind of structure within them that makes a difference to how they move and things like that. But when we're rendering things, we care not about what's inside. We care not about what's inside this teapot. I mean, we'd probably care about the bottom surface of the teapot, but we don't care that there's maybe some liquid inside, that if in a physics simulation, we might actually care about there being liquid inside and stuff like that. But all that we care about is that if this teapot is an opaque teapot. So we've got a lot more trouble with my glass here, which is transparent. But if it's opaque, that it can't be seen through, that the only thing we need to think about is the outer surface of the model. So we're actually getting closer to this idea that if we're looking at the outer surface of the model, then we have an inside and an outside of every model. So what we're going to get is that every triangle now actually has a front and a back. So if my hand here, yeah, I'll just use my hand. I was going to look for an object on my desk, but I'm just like, I'll just use my hand. If my hand here is made up of triangles, we will never, ever see the back side of the triangles that are on my hand here, because the back side of these triangles are some weird concept of the inner layer of my skin. Right, and we would not be modeling the inner layer of my skin. The inner layer of my skin doesn't necessarily have a texture or anything, because it's not visible, because if we were to look at it from the other side, we'd see the front of other triangles, which is the palm of my hand. We'd never see the inner layer of skin that's here or something. So triangles are now going to start having a front and a back, a visible side and a side that should not be visible. And I say should not because bugs can make things visible. I don't know if you've ever seen this, where you've accidentally in games got your camera stuck inside a person or something like that, and you see this partial rendering of the inside of them, in a sense, because a lot of the triangles there are by definition not visible because we're looking at the back of them rather than the front of them. And the other thing that changes a bit here is not just the fact that triangles will have an open, like a visible side and a shouldn't be visible side, as in, you know, like the surface of an object should be visible from the outside, but how could you see it from the inside? It's meant to be a solid object. You're not meant to be able to get inside it, right? So triangles are going to have that front and back. But we're also going to be treating our vertices differently. So the way that we've been thinking of our vertices up until this point is that they're corners on shapes. So we've very much been looking at corners of triangles and corners of rectangles. We're going to be expanding on that idea and not thinking about them as corners anymore, but thinking about them as positions on a surface. So on my hand here, there might be a whole lot of verts. And it's like, you know, humans, like, we've got so many curves all over us, right? We don't have any flat surfaces. So it's actually really annoying modeling us because you can have lots and lots of verts. So say I've got, like, you know, 50 verts on the back of my hand here. Each one of those is representative of a position on the surface on the back of my hand and how it may react to things. So is it curved? Is it flat? Is it sweaty and reflective, or is it not? It's mapped to a texture, which is going to be like some kind of photo or painting of skin, and it'll be mapped in some way to that, so that this can be textured correctly across that. These are really interesting and important properties, but we're not going to be looking at them today. I just wanted to bring them up so that you have an idea of where we're heading soon. So when we're going to start thinking about how we use the surface of an object to tell what color it's going to be, to bounce light off it and stuff like that, you start to get to the idea that vertices are not corners, they're just points on a surface. But we're not going to go into that today. We've got more work to do today on the basic idea of objects in a 3D space first. So I'm going to talk about objects in a 3D space, how we put them together. But more importantly, the one thing, you know, when I had that joke about 2D and 3D being the same, there was one thing that was actually very different here, which is how we look at things. So up until this point in your 2D, everything that we've been doing is saying this is a flat surface. We exist on the Z-axis. Like, we're literally like looking at things down the Z-axis as if the Z-axis is pointing straight at our eyes and doesn't exist. Well, we can't see it because it's a single point pointing at our eyes in a sense. And that's the only way we were looking at things. Once we're in 3 dimensions, we need to have a viewpoint that can see things, and it's very rarely just going to be sitting on an axis looking at things. Pretty much any game you may have played, especially like nearly all 3-dimensional games, have the idea that either you're a person in the scene or you're an observer looking down over things and stuff, depending on the scale of the game itself. And that's always going to be a virtual camera that's in the scene. So once we've learned about virtual cameras and how they see things, then we're going to go back to this and go into more detail about how objects are built and stuff like that. So I did want to talk about something though. And I did sort of mention this, that we are going to be looking at objects and how they are placed in 3-dimensional space. So I want to introduce this concept to you of different coordinate spaces and local and world coordinates. So local and world bold in each of these points here. So I've drawn this idea here of this is our X, Y, and Z axes. So we're kind of used to these now, at least the X and the Y. We've been using these to just put objects somewhere in our visible scene. So a lot of what we've been doing is just the idea of stuff is visible between between 1 and -1. So I was going to say 0 and 1, 0 and -1, right? So there's this kind of square that we can see things in. And even if we're squishing it to a different window size, the coordinates are still that 1 and -1. But that's our world coordinates. Our objects could have their own coordinate space. So especially when an artist is creating objects to then give to us to put in a scene, or you're putting together an object that you want to use, the object can actually have its own coordinate space, its own origin. So if I'm building a cube, I'm not necessarily going to build it by figuring out exactly what dimensions and what exact coordinates each of these verts needs to be if it's tipped on an angle and off in the distance or something to make a cube. What I would usually do to make a cube is I would build it at the idea of an origin at 0, 0, 0. So it would have each of its verts being like 1, 0, 0, 0, 0, 1, 0, 0, 0, 1 and stuff. And then you'd be able to build a cube really easily, and then afterwards you go, okay, put it into the scene in the right position. So we would shrink it to the size it needs to be, shift it off into the distance and stuff like that. So it would have a position, which is its origin. So where its 0, 0 had been when it was created, could be a point in space in the world where it's going to be. So I could say, just move this away from 0, 0, 0 and place it off in the distance here. That's a translate transform, right? We've seen that already. I could translate something into the distance. I could also say that this thing's going to be rotated. So before I shift it out there, I could rotate it. So I could say, instead of the y-axis being up for this thing, I'm tipping, just got to match up my camera to what's on the screen. So I'm tipping my object over to the side a little, I'm tipping it back a little, or something like that. So I've rotated that object before I've translated, which means its own coordinate system is tipped. It's relative to, so let's say I've got the world coordinates and its coordinates. They're not going to be exactly the same, right? Because they should both be right-handed, but you know. So I've moved it off into the distance and I've tilted it. So if it has its own set of coordinates, its own axes are actually vectors that exist in this world space, because each of its own axes, see its y-axis here is definitely different from the y-axis. That means the y-axis is actually a vector saying I go in a different direction from this. So relative to this thing where the y-axis is 0, 1, 0, it's a vector that points straight up and only has value in the y, in the y of this world coordinate space. This vector might not just have y coordinates, it might have x coordinates as well, it may have z coordinates. I didn't draw this at the detail level where you can see exactly how it's rotated. So what we get is this really interesting thing where each object has its own origin, where it thinks of it as a 0, 0, 0, but in terms of the world space, we think of it having its origin somewhere in the world space. So we end up with a transform that can go between the local idea of the object having its own coordinate space and where that coordinate space exists in the world space. So we get into this question here of like, what is a matrix transform? So up until this point, I've said to you that a matrix transform is something that moves something, or something that reshapes something. Like it transforms an object. But what it actually is a single 4x4 grid of numbers that represents how this object, as if it had been, so for example, created at 0, 0, 0 as a basic object with basic shapes and sizes, what we would do to then put that into our world in a different place. So it's actually a transform that takes us from the local coordinates of the object itself and places them into the world space. So the matrix transform is capable of taking something that was, created at a particular scale. So for example, I've created a crate that's going in an environment, but because I put all my love and effort into this crate, I did it at such great detail that the crate is 10 meters by 10 meters, and I've got all these perfect details, textures and stuff like that. But when it needs to be used, it needs to be transformed before it can be used in a scene. So what happens is we would take that 10 by 10 meter crate and we would scale it down, and we'd say, in our scene we've got all these rooms and stuff like that, and then what we would do is we would place this crate at a particular coordinate system, rotate at a certain point, and scale down to fit the scale of the world. That's what the transform matrix is going to do. But the difference is it's not just moving these things around, it's actually recording what that shape ends up having as its set of axes and its origin. So its origin point is going to be where it ended up in the scene. Its axes are going to be shorter because it's scaled down from the size of object it had been, and maybe these axes are moving in different angles. But each of these axes can now be recorded as a vector using world coordinates. So from the world coordinates, they're a directional vector, and then they have an origin somewhere as well. So instead of thinking about the transform moving an object or changing an object in the world, we can think of it as transferring an object from its own coordinate system that it had, the way that it was built. So its verts were, you know, relative to 0, 0, 0, but once we transform it, then they're moving into a different coordinate space. So the transform is actually shifting objects back and forth between their local coordinate space and their world coordinate space. Interesting thing about this is the way that the transform is constructed is actually really, really easy to read. So this is the identity matrix. The identity matrix is actually made up of 4 vectors, and this extra homogeneous vector here, which is used to help it transform things. But the x-axis is actually these 3 numbers here. The y-axis is these 3 numbers here, and the z-axis is these 3 numbers here. The origin is these 3 numbers here. So the identity matrix in our world defines the x-axis as being a vector of length 1 pointing only along the x-coordinates. That's correct. That's exactly what we think an x-axis is. X-axis. The y-axis is a vector of length 1 that only has value in the y direction. So it's pointing straight upwards, and it's not tipped towards you, so it has no z-axis, not tipped towards the x, it has no x-axis, so it's going straight up. The z-axis, likewise, is going straight forward towards you. The origin of that sort of this set of axes is 0, 0, 0. So that is the center of the world. So this is why this is the transform we start off with before we start multiplying things in to move objects to other places or to convert something to another coordinate system, because this is actually the basis of the world coordinates. They start at 0, 0, 0. The x-axis goes along x, y-axis goes along y, z-axis goes along z. But other transforms, transforms that are basically attached to objects, are going to define the properties of that object by where do their x and y and z axes aim, and how long are those axes. So the length of the axes, and you can see here, remember, the scale transform scales in x and scales in y and scales in z. So if I wanted to change one of these 3 numbers, that would actually change the length of these axes. And if it changes the length of these axes, it will stretch the object in those directions, exactly what the scale does. Scale was not changing it wasn't stretching your objects. What it was putting them into a different coordinate space where their axes had a different length relative to the world axes. And so if the axes have a different length relative to the world axes, then they end up stretched in that direction. So that's kind of what scale's doing. So we're building up idea that the transform is not just a set of random numbers that shifts something or changes something. The transform is actually the definition of a different coordinate system that can exist within the world coordinate system. So, I hate it when I do this. I have a good idea about what I'm going to teach, and I go, I'll teach about the scale, and then I make a slide for it, and I talk about it without going to it. Okay, so anyway, this is it, right? The object x x-axis is twice as long as the world's x-axis. So in effect, this is what stretches the object. What we're saying is the object had a different x scale than the world, and so when we transform that object into the world, it gets bigger. It gets twice as big along the x-axis because its x-axis is twice as long as the world's x-axis. Translate can do the same kind of thing, where if I say have an object where its origin relative to the world, we want its origin to be somewhere else. So we want its origin to be at the coordinates 5, 6, 2. So it's just sort of, where are you? From your perspective, it's off in this direction here. I'm having to mirror everything. I'm watching the video to see if I'm mirroring it correctly. Anyway, so if we're not scaling it by anything, and we're also not rotating it because there's no other changes here, so its axes are not tipping in any other direction, so it's just moving. Its axes remain similar vectors to the world axes, but its position ends up somewhere else. This is the 3 coordinates of the origin of the object. So the translate transform was not necessarily moving things, but what it was saying is the origin of the object, instead of it being at 0, 0, 0, in world coordinates, the origin in the object is at 5, 6, 2, and then all of the points, all of the verts in the object relative to the object are in the same scale, you know, and they haven't been rotated or anything. So that's what the translate transform is. So what we end up getting once we've done that is we can compose multiple transforms together. So we take all these transform matrices and we multiply them by each other. So we can scale something, we can rotate it, we can translate it, we can end up, there's even other transforms. So if you want to look up, there's this other one called the shear transform, which does weird things you can't quite do as easily with the others. So the shear transform can take like a rectangle and stretch it out into like a trapezoid. You could do that by rotating and scaling something and then rotating it back, but it's a bit more fiddly. So the shear transform, it's just a funny little thing where you can, it's like scaling and translating at the same time. So the thing about this is, if we multiply all these transforms together, we're never going to lose any information from any of the transforms. So they're all just going to get combined without losing any information. The order is still important, but like, you know, we know that already. We've seen the order being interesting, but all of that information together, after it's all been applied, we can still read it. So we can still look at that transform and say, this is a set of 3 axes for the object. And so those 3 axes might be vectors that are not just like, you know, 1, 0, 0, 0, 1, 0, 0, 0, 1. They might have really complicated numbers in them to say where they are. They're still going to be right angles to each other because that's the way they're going to work. But they could be tilted. One could be longer or shorter than the others to change the shape of the object. And then the 4th column there is going to tell us where the 0, 0, 0 for that object ended up in our world. So where we place that object. So we can take this, and so we can take an object that existed in a particular coordinate space, so it was built in a coordinate space, and then to place it in our scene, we said, okay, we need to shrink it, we need to move it over there, we need to rotate it. Okay, so we put all of those matrices together, and we end up with a transform that says this is exactly the kind of spatial identity for this object that we've created. So this is where it exists in our world. And that thing is known as the model matrix. And it's the thing that takes it from its own coordinate space and it puts it in the coordinate space where we're going to be building our virtual world. So people are saying, oh, hello, John. I'm not sure if you're an ex-student who just saw this, because I'm doing my lectures public so people can see it. Bob's saying, is this just a chain of matrix transforms? Yeah. So we chain a whole bunch of matrix transforms together by multiplying them. And mathematically speaking, the one at the end of the multiplication, the one closest to the vector, is the one that gets applied first, and it goes backwards. We're going to multiply all these together, but what we're going to end up with is not just like a a jumble of numbers that says how to transform something that we're just going to kind of black box and not understand. What we're actually going to understand now is that those transforms are made up of an x-axis, a y-axis, and a z-axis for that object, and a point in space where that object has its origin point. So we get a little bit more information about what our transforms are doing like that. So Logan's asking, when you move your character in a first-person shooter game, is it translating in z-axis or scaling in an x and a y axis? It will be moving, so it will actually be translating. The scaling is something that will happen based on the idea of your perspective in the game. So we're going to get to that on Wednesday. We'll be talking about that and how that works. So what we're getting now is this idea of like the model matrix, which is also considered the transform of an object. So we're going to start having objects existing in space, but they'll be built in their own local coordinates. And their transform is going to define where and how they're used in our world. So we're going to start to get the idea that objects and transforms are inseparable. Like, you don't have an object without it having a transform, unless the object is, say, the world itself. But even then, it has a transform. It has this transform, which says that my x, y, and z axes are the genuine coordinate x, y, and z axes, and I start at 0, 0, 0. You know, so even the base kind of location that we put everything else into still has a transform. It's just a transform that doesn't necessarily change its numbers in any way. Okay. 4:55, this is a good time for a break. Talking about the Matrix. So this is a photo. So this is where I won't get a copyright strike because it's a photo and I have image credit there for it. I said 1998. I was wrong. It was 1999. So important films with CG. This one is a little bit important to us because it was actually made in Sydney. So you may have potentially somewhere around the place, I mean, those of you who are in Sydney may have met someone who actually worked there. They have t-shirts like this that say Animal Logic. Does that say crew? No, I think it's on the back. Can you see that? Yeah. So, I didn't actually work on Peter Rabbit. I just have it because I had family who worked there. The Matrix was actually rendered in Sydney by this company called Animal Logic. I've met the person that did the scrolling text code, and apparently, like, it's just stuff from a sushi menu because he doesn't actually know Japanese. So he doesn't. So if you actually pull it out and see a lot of it, it's actually like you can actually find words in there that are just food. Another thing that is my little claim to fame that I like is that one of the machines that actually rendered the CG in the Matrix is in the lobby of the K17 building, and the reason why it's in CSC is I found it in our storage at iCinema, which is a research center for interactive cinemas like VR and CG stuff that I was working at UNSW. And we found it there and figured out that this was actually a machine that had been donated to us by Animal Logic, and it was like, wow, we actually have one of the machines that was used to make the Matrix. And so we brought it to CSC and said, do you want to put this in the foyer, because it sure as hell doesn't run anymore, but it's like it's a piece of history. So it's the size of a fridge. It's massive. But yeah, it's a fun little anecdote. Okay. 4:58 now. We will come back at 5:03 after a 5-minute break, and we will continue using some of what we know now about how to put together transforms and three-dimensional transforms and objects in their own three-dimensional coordinate space and stuff like that, to build our first idea of a 3D object in a particular position by making a 3D, doing all the maths, the matrix maths behind a camera in a 3D space. All right, back in 5. I'm back. Funny little point in chat there. Someone was saying, imagine being able to go to the CSC lobby, and people saying how much they miss it and stuff. I think I said this in a welcome to students that I did in early mid 2020 or something. It was for an open day or an O week or something like that, where I said, we're not in UNSW at the moment, but UNSW exists in our hearts. So wherever we are, that's where CSE is. So all over the place where we are, CSE is right here. I stole that. It's from what's the movie? 36 Chambers of Shaolin or something like that. It's a really, really old Chinese kung fu film where it's just basically the Shaolin Temple had been sacked and they said, but where will we go? we're leaving the temple, and then the abbot of the temple says, no, the temple exists here. Anyway, yeah, the true graphics were the friends we made along the way. Yeah. Jason is asking about texture mapping units. Oh, about the hardware, what the GPU does. I don't know exactly. I haven't really picked at all of the hardware in the GPU and exactly what it does. But what you're saying there sounds right, in that the texture mapping unit is doing the texture sampling parts. The streaming processors are doing a lot of the floating point multiplication stuff. And the memory is containing stuff like vertex data, not just vertex data. The memory is containing all of your buffers. So your buffers are including vertex data, textures, index buffers, things like that. Frame buffer as well. Frame buffer is vitally important, because if you don't have a buffer for the color of all the pixels, then you don't know what you're sending, what information you're sending to the monitor itself. So you can really think of the RAM and the graphics card as having to do a lot of different heavy lifting. Got a little friend has come to say hello. I'll just leave that there for the moment. Okay, so moving on, we're going to start to think about cameras and viewpoints. So there's a lot of sort of thinking that's going on here, which is why I ended up doing the Matrix for today, because we're delving into the Matrix. Today's quite a math-heavy lecture, but I actually still find it quite exciting, because seeing how we're going to put together a coordinate space for a camera to exist in and stuff is going to give us the capability to look at our scene from a certain direction. And then with that capability, we are then going to go into, on Wednesday, how the camera actually sees things. So, cameras as objects in a scene. So this is an interesting thing, right? Because the camera can, yes, definitely exist in its own coordinate space. So that means it has its own transform. The camera has a transform. But the weird thing about it is there's no vertices for the camera itself. So the camera itself obviously doesn't have verts, it doesn't have textures, it doesn't have an existence in a sense of the concrete objects that we've been creating, like the triangles and rectangles and stuff. So it's not a 3D model. It's different from a 3D model, but it's the things that allows us to see all the 3D models. So we think of it as a viewpoint that exists in the world space. We're going to talk more on Wednesday about how it actually sees things, because what it does to actually see things, it needs to be able to feed stuff into the OpenGL pipeline. And in order to feed stuff into that pipeline, it needs to know where things are. And for something to know where things are, it must have a transform in the space, because without a transform, it does not have a relative viewpoint on the other objects. Right, the transform gives it a concrete location somewhere in our scene. So, some of the rules, I guess, that OpenGL will be using to do this is it will be using the camera's Z-axis to tell where the camera is looking. The Z-axis is very similar to the one that we've been using so far. If the Z-axis points directly at your eyes through the screen, that's the same thing for the camera's Z-axis. So the camera will actually have a Z-axis that is pointing into the lens. It's not real, there is no lens, but if there was the virtual lens, the Z-axis would be pointing into the lens and out the back of the camera. And so that's the direction of the Z-axis, and we're always going to be looking along that axis when we're trying to see where a camera is looking at things. The camera transform, which is the thing we're going to create now, instead of it being a transform for an object, which puts the object into our scene in a particular place, is actually going to do the inverse of that. So what it's going to do is it's going to say, here's the camera. The camera now owns the scene. So we will take our world space and we will transform it using this camera transform into the camera's space. So the camera's coordinates will be like the last set of coordinates the vertices get before they get turned into They get rasterized into things. It's not exactly the case. There's other things that's going to happen, but you can think of it that way, that what we're going to do is today we're going to put together a transform that allows us to take all the verts in the scene, no matter where they are and stuff, and say, if I have a camera here and all my verts are here, I'm going to transform everything so that they end up being viewed from the camera's perspective. Bob's got it exactly there. The camera is like the new origin. Yeah, so we're going to make a transform so that the camera kind of becomes the new origin. But when we're working with our scene, we're going to be thinking of our camera as an object in the scene that we're going to use for things. So the way that it kind of works is, for example, in a first-person game, the camera exists in this idea of where the character's head is, and it's going to move through the scene. So it's moving through the 3D world. But every time we want to see what the camera can see, we're going to transform everything so that the camera sits basically at the origin of its own world, and it sees a particular area. We're gonna go into more detail about how the camera sees things and what it sees and stuff, but for the moment we're going to actually try to get this camera transformed to exist so that we can actually mathematically put things into the camera's view. So these are roughly the steps of how we're building the camera transform. This is from Learn OpenGL as well. I actually edited it a bit because their coordinates here was 0, 0, 2, which meant the camera should have been on the Z-axis. So I edited this just a little bit for correctness. We're going to be using some of these numbers here in the example. I will probably, I think I'll grab Microsoft Paint out and I'll draw these things as we're making it so we don't have to keep referring back to this slide. But what we're going to do is we're going to build up the camera transform bit by bit. So let me just replicate some of what was there. So we've got our X and our Y. Obviously none of this stuff is to scale. Like I can't do this stuff to scale because I'm trying to give an idea of a 3D space in 2D, right? So it doesn't particularly work that way. But if my camera, if the position I want for my camera is 0, 1, 2, then it means my camera is kind of here. So I'm going to draw the universal idea of the virtual camera. We'll always end up drawing like this. We'll always end up drawing cameras looking like this because it doesn't exist. It has no verts or anything, but we need to just give it an image that that makes it vaguely look like something that is capturing footage. So there's our camera. And at the moment, the position that we want for our camera is 0, 1, 2. So that means it's backing off along the Z-axis, backing away from the origin. So that's okay. We're probably going to be looking at something that we've built near the origin. At the moment, we're not even caring about what's there. So we're just saying this is where we want to place our camera. Also, we're going to move the camera around if we want to. So this is just how we're going to build it for starters. So if the camera is at this position here, let's start working on how to piece this together. So the first thing that we can do is camera position, placing the camera in a position. We can put this in our scene using translate transform. And we've seen already that the translate transform gives us the origin, the coordinates of the origin of the camera. So if I want my camera being at 0, 1, 2, it's really, really easy for me to make a transform that puts the camera there. Like, so it's a 1, 1, 1, 1, bunch of zeros. I just put the X, Y, and Z coordinates of where the camera is going to be here. So it's got 0x, 1 in Y, 2 in Z. That's one of the transforms that I'm going to use. So this translate allows me to say the camera has its origin at 0, 1, 2 in the world coordinates. So the camera's going to be saying, this is where my 0, 0, 0 is, and the world's going to be saying, all right, from our perspective of our 0, 0, 0, your 0, 0, 0 gets you this transform here. So this means, as I said here, our camera is just along and above the z-axis. So it's 2 spaces along and 1 above. We don't really measure units as a particular measurement. It really depends on the design of the world that you're in and what kind of coordinate space is being used. Plenty of times when we're working on these things, if we're simulating the real world, a lot of the time our coordinates are going to be something like 1 meter per point, but there's no reason why. It's an abstract space. You can do anything you want with it. So that gives us a position, it gives us a transform to start with. So we've taken our identity matrix, which is not changing anything, and then we've said we could actually have said that we're translating via this X and Y and Z here. So then we're going to start building up what we need to know exactly what the camera is. And to know what the camera is, we need 3 axes. So we've got a position, we have an origin, but with that origin, we have no genuine information about the camera. We cannot transform anything to the camera's perspective by only knowing where it is. Because if we don't know where it's looking, we don't have any information about where the vertices are meant to go. And we don't know what scale the camera is in, so we don't know whether we need to blow up our world or shrink it or anything like that. So we need 3 vectors, and those 3 vectors are going to build up the axes for the camera. So the first vector is going to be the z-axis in a sense of the camera. We call it the camera direction. And it goes from where the camera is looking to the camera. So as I said before, the z-axis most of the time in graphics is pointing out of the screen towards you. So if we want a z-axis, not there, here, a z-axis that makes sense for the camera, we want the camera's z-axis to basically be, at its origin here and pointing out the back of the camera. And you could think of it just the same as a, where's my cursor? As a vector that points from the origin to the camera. That should be a really easy clue, because if I want a vector that points from the origin to the camera, I can just minus the vector. So if I want to point from the origin to the camera, all I need to do is say origin to the camera says I've got the camera's location minus the origin, which is 0, 0, 0. And then I get a vector that aims at the camera. 0, 1, 2. So that can be my vector. That can be one of the vectors in my axis, because it's going to be the exact direction that the z-axis is. It's not always going to be this simple. Sometimes we're going to be looking at an object that is somewhere else in the scene. Just drawing a spongy cube. I don't know what it is. Let's give it a smiley face for fun. Right, so if I was looking at that spongy cube, then this subtraction wouldn't be that simple, but it's still pretty simple that we're just going to subtract those numbers and we end up with a vector that says this is where the camera is looking. Just remember, it's not a vector that is the way that the camera is aiming. It's a vector that is from the target position aimed at the camera. Yeah, Wave Plasma was just saying, does this apply if the camera isn't pointing towards the origin? 100%, as I was saying. So we could totally say the spongy thing is at, I don't know, 5, 5, 0. So it's at the middle depth of the Z, but it's across a little bit on the X and up a little bit on the Y. And then we would have something like 0, 1, 2 minus 5, 5, 0 would equal to, what are we looking at here? -5, -4, 2. So our look vector, oh, it's not really a look vector. Our camera direction vector would be pointing then from the center of this object, which I've just given it a nose, to the camera. So wherever you want the camera to look, you just minus where it's looking from where it is. And that will give you a vector that aims at the camera from the object. So it didn't have to be the origin, could have been anything. But the origin keeps it simple so that I can do this without having to do my maths in real time and stuff. I mean, at some point I may have to do like a cross product or something in real time, but I'm going to try not to. Because I've got 40 minutes to go through this. So that gives us one vector. And that vector gives us one of the 3 axes for the camera. So I'm just going to go with the green one, not necessarily the complicated one here. Keeping it simple, if we're looking at the origin, camera location minus what we're looking at gives us, in this example, 0, 1, and 2. So this gives us one vector for our axis. But before I start building up all of these vectors and things like that, I want to talk about the difference between a vector that represents a position and the vector which represents a direction. So when we're going to be doing things like multiplying things out with directions and things, we don't want to get confused and start using vectors as if their distance is meaningful. So the distance is meaningful in a vector if the vector is a representation of a position somewhere, right? Because the position is a distance to the origin, and it's very, very important how far away it is from the origin. Whereas the direction aimed at the camera, it is not important how far the camera is from that object. It is only important the exact direction that the camera is aiming. And this is where we will normalize our vectors. So, I was taught this like, I don't know, like 20 years ago when I did graphics. It's like, when in doubt, normalize the vectors. Like, if you're doing anything with like cameras, lighting equations, and just normalize all the vectors. That's good until you normalize one of the points, and then you're in trouble. But normalizing the vector roughly means make the vector length 1. And that is functionally what normalizing does. And so what we will do to normalize a vector is divide it by its own length. So we can find the length of a vector because a vector is made up of a horizontal component, a vertical component, and a forwards, backwards component. The X, Y, and Z components, which means that the vector makes up a triangle, basically, like a Pythagorean triangle. So you can actually normalize this by saying it has length in one dimension, length in another dimension. This one's easy because it's only got 2 dimensions worth of length, so it's just a triangle. And so the hypotenuse of the triangle is the length of the vector. So if we do, like triangle maths, right? The hypotenuse is the square root of the square of the 2 sides. So if one side is length 1, that's 1. The other side's length 2, square that is 4, so root 5 is the length of the vector, and if we divide all of the components of the vector by its length, then this resulting vector, 0, 1 on root 5, 2 on root 5, is exactly length 1. I am not going to go into the exact details of using this vector like this, but we're going to remember that this thing's not actually 0, 1, 2, it's going to be 1 on root 5, 2 on root 5. And you'll notice in all of your code examples and stuff like that, that we're going to be using GLM normalize on our vectors a lot of the time to keep them length 1. Our axes for our camera are going to be of length 1 just because our camera is not necessarily going to be scaling the world yet. We will potentially scale the world and do other things with it. But for the moment, we're going to normalize all our vectors. Vectors are going to stay length 1, especially in this building of a camera thing. I don't know who Minecraft Steve is, Conrad. I assume Minecraft Steve is someone who draws things. Okay. So we're going to start leveraging things to make other vectors. So one thing that we can think of is the camera is going to be aiming at something, which means we've got that aim vector, but we need to get this vector that goes to the right and another vector that goes up. We can start building these things using the idea that a cross product of 2 vectors will get us another vector. Oh, Simon, I'm sorry. Yeah, I mean, people have found out that I don't really know that much about Minecraft. There's several streams of me learning Minecraft and people watching me and laughing at how bad I am at it at the beginning. But there was also these really wholesome streams where like, he's starting to get it. He's building a house and stuff. Anyway, let's go for the idea of an upwards vector. I'm gonna tell you what it means and then how we're going to use it. So we as humans have like this kind of, oh, Minecraft Steve's the default skin, right? I should have known that. Anyway, Cheeseburg, yes. That was the town that we made. It was a lot of fun. Okay, we as humans in this 3D space that we exist in have an assumption of gravity. So we have an assumption that there's an up. There's an up and a down, and the up and the down is so fundamental that we can just feel it. I think that the only people who have a good understanding that the up and down is sort of a construct is people who have gone to space. Or maybe people who do deep sea stuff, but even underwater you can still tell which way is up and down by gravity. Your inner ear can still tell which way is up and down. So it's really only people who've gone to space. So one tiny 0.1% of the population understands that the concept of up and down is only exists on the surface of a planet, but we really assume it. So what we can do is we can expect the camera to stay upright. Cameras do shake and turn sometimes in films and stuff like that, but only for very specific effects. And only to intentionally disorient you. So we're going to say, okay, there's an idea of an up and down. So we can keep this really, really simple in our world. So we're assuming for the moment that our world is using the identity matrix as its transform. So its y-axis is 0, 1, 0, pointing straight up. So we go, okay, let's just use that. 0, 1, 0. And so the question I have for you is that fine? Can we just use that as our axis? Can we use 0, 1, 0 as one of the axes of a camera, that up axis for the camera? And I say, is this an acceptable axis to the camera? And you should know that if I ask a question like that, the answer is nearly always no. I'm not going to ask you a really, really specific question unless I think that some of you might say yes, and then I'm going to explain to you why this is not the case. So, if my camera is here and my world up vector is just pointing straight up, can I use it as this axis on my camera? And it's like, okay, let's think about what these axes have to be. A set of 3 axes have to follow this property called orthogonal. Orthogonal means they're all 90 degrees from each other. This is exactly 90 degrees from each other. They're exactly perpendicular, no more, no less. Because without them being perpendicular, they do not make a uniform world. Like if one of them skewed at an angle, that means the whole world is going to be skewed in a strange way, right? And we're not necessarily wanting yet. I keep foreshadowing what we're going to do with cameras. We're not skewing or transforming the world yet with this camera. What we're doing is trying to just move all the coordinates into a viewpoint so that the camera is looking straight at these things along its z-axis. So we need all 3 of the axes for the camera, no matter which way the camera is aiming, to be 90 degrees from each other. So if we were aiming exactly along a flat plane, right, then yeah, okay, we could technically use the world's up vector as one of our camera axes. But the likelihood of us having a camera that only ever looks flat along the plane, super, super unlikely. I mean, yes, if you look at Doom and Wolfenstein, early kind of pre-3D games, they do that because they didn't necessarily have the capability to rotate up and down their camera perspective. But we're definitely doing that. We're starting with that capability. So it's incredibly unlikely that the world's up vector is going to actually be our camera's up vector. So I've been careful to I'm just going to try to name these differently. So the world's up vector, camera's up vector. Each of them has an up vector, but they're not going to be the same. So why did I go to all this trouble to think up this anti-gravity vector, the vector that goes up the y-axis? The reason is we're going to use it to make one of our axes, even if it is itself not going to be one of our axes. So let's go back to here. So I'm gonna make it a sort of a pale blue like this. This is my up vector, and my up vector is going to be 0, 1, 0. This is basically me doing whiteboard teaching, but I don't have a whiteboard. I don't even have my tablet computer. I was dumb enough to leave it in my office at UNSW, and I can't be bothered doing all the paperwork to be allowed to swipe into the building to go and pick it up. Anyway, I'm okay at Microsoft Paint, right? People are always like, he's okay. He's not good. All right, so this is my up vector. Because the camera's forward vector is not flat, I can't use the up vector. But what I am going to use is the idea that with two vectors, I can make another vector which is guaranteed to be 90 degrees to these two. So these two vectors, the one coming out of the camera and the one pointing straight up, form a plane. So you can see the side of the plane here by me moving my hand. So it would be a plane like this, right? The camera's looking along that plane, and it knows that up is along that plane as well. If we make a vector that comes straight outside that plane, there's only one possible vector that is right angles. Well, there's two. There's one in either direction. But really, there's one line that is perpendicular to that plane. If we find that one, we'll have one of the three vectors that makes up the axis of our camera. So what I'm looking for is a way to take two vectors and get a third one that is 90 degrees to the two of them. And this is the thing that's going to be called the right vector. The right vector has to go to the right of the camera. It's the x-axis of the camera, so it's not the wrong vector. The world up vector is the wrong vector. So if one of those axes is going to the right, it's like it's going across our screen from the left to the right. How do we create a vector that's right angles to two other vectors? We use cross product. So cross product, I'm assuming a certain amount of memory for your linear algebra here, or if not, a certain amount of memory of your linear algebra. At least you can look this up if you need to. So doing the cross product on this world up vector, which we could not use as one of our axes, but it still gives us enough information. Cross product that with the camera direction, we get our right vector. So cross product, if you remember, so I'm not even going to go through the maths of this because you can look that up, but the order that we do things makes a difference for the cross product. So first vector, you can do this with your right hand. It works with your right hand. Hopefully everyone actually has, if you don't have a right hand, you can imagine, right? So someone here doesn't have a right hand. You've got a right paw, don't you? She's just meowing at me. Okay, first vector, second vector, result vector here. So if my first vector is my up, second vector is the one pointing out the camera at you, third vector is this one, and you can see on camera, this is going to the right. So this is the correct vector. So I'm going 1, 2, 3, and I've just shot you with finger guns. So there you go. So if I take the cross product of these, at the moment I'm just using these not normalized, because we're still going to get the correct direction even if they're not normalized, because that made my calculations here easier and I didn't have to write all the square roots and stuff. So I take my 0, 1, 0, I cross product that with 0, 1, 2, and I get 2, 0, 0. I'm not going to mechanically do the cross product, but if you've seen it, you like multiply pairs and then add them. No, multiply pairs and minus them from each other and stuff like that. You can look up the procedure for cross producting, or you can get GLM, the GL Maths library, to do cross product for you. But either way, we're going to get the result of 2, 0, 0, and we can normalize that to 1, 0, 0. So strangely enough, our right vector has ended up being a copy of the x coordinate. So where are we going to draw some maths here? So I'm going to say right is equal to up cross direction. I'm just going to call it dir because of the camera direction vector. And that means right is going to be 0, 1, oops. It was 1, 0, 0. So this vector now comes out here, and that's our right vector. So we got 2 out of 3 now. So this is a maths gang sign, yeah. I remember doing that, like the way that we studied for maths was like 3D loser. So it's like, you know, like people like insult people by going, they're a loser, but like if you're a mathematician, then like we're like Like those of us who do linear algebra, we must be even more losers because you can tell we're a loser from any direction. You can look from either side or from above, and you can still tell that we're a loser because we're a 3D loser. But also, that's the only reason why I remember the right hand rule well, because of the 3D loser thing. Okay. We now have our right vector. So we have our camera direction vector, we have our right vector, and now for us to have a proper coordinate space for the camera, we need our third vector. And we've already ruled out the world's up vector as a possibility, because if you look at this, the camera's aiming downwards a little, or if it was aiming at this object, it's aiming over that way a little. If it's aiming at that object, we wouldn't have gotten this right vector, by the way. So we're just going to leave it aiming at the origin. I should actually... It's too much effort to rub that out. You know we're not using that object, right? So we're just aiming at the origin. We know that if we're tipped down, the directly up vector can't be it. It has to be also kind of tipped forward. Oh, Daniel's asking, what if the camera direction is like directly up or directly down? It can still get a set of coordinates like that. If you just go through all of this maths, you will still get a result out of that. But one of the issues that you're going to get is if you chose the world's up vector as your up, and then you're pointing directly along it, your cross product for your right's not going to work. You may have noticed this, because in pretty much no game in existence can you look directly upwards. You can look mostly upwards up to like within 1 degree of it, but you can't even go past up and look back. Like you can't tip your head up and over to look back behind yourself or anything. Like all games will have a limit for how far up and how far down they go, because the second the camera matches the up vector, either in positive or negative direction, it stops rotating properly. So I'm not gonna go into super detail on that, but it is 100% a thing that happens. If you look too closely, if you stare into the sun, you will go blind. Literally, our cameras do that. If you match up your direction vector with your up vector or your down vector, you will break the rotations. That's actually not exactly the same reason that this is here, because that's actually a rotational issue. But either way, if we line up our axes with certain vectors in a particular way, we end up multiplying a bunch of things by 0 and then having no values with which to then escape that particular rotation. So yeah, but we'll go into that later, because I think that's a detail we could talk about. Simon's actually... I'm glad you remembered that, because I've forgotten the name of it, which is gimbal lock, which is this idea that you can get stuck unable to rotate out of certain positions. So you can look it up. It's really interesting, because it's something that's actually a physical property of rotations if you're rotating specifically around the X, Y, and Z axes. Someone asked earlier today about quaternions. Quaternions do solve that problem. So quaternions can rotate to any arbitrary direction around any arbitrary axis, and they don't get stuck. They just involve... You know, I was talking about thinking about 4 and 5 dimensions? That's how you learn about quaternions, which is why I'm not doing it in the introductory course. Yeah. Okay, so let's continue what we're doing here. We've got 2 axes. We've got the camera direction axis and the right axis that we used by taking the world's up vector and cross-product it with the camera direction vector. So we have 2 axes. These are 90 degrees opposed to each other now, which is perfect. And we need a third one, which is going to be 90 degrees opposed to both of the other 2. And I could say, oh, how could we possibly find the third vector if we have 2 vectors and we want to make them 90 degrees opposing each other, right? It's actually easy now, because we know how we can do this. We can just do a cross product. So we've got 2 vectors. We've got the camera direction and the right, and we need the up axis, which means that, following my 3D losers right hand rule, if I want up to be my result, then I need... Oh god. I just looked at the camera and I'm just like, I'm just being very rude to my students. I have to do it. I have to do it to show you. People are going to screenshot this now, aren't they? Okay, the right hand rule. So if we start with the camera direction, oh no, it's going this way. It's okay, it's going this way. The camera direction is the first axis, so that's the first one. The right is pointing to the right, so I know that these are the two that I have, which means the third one that gets created is going to be on my up vector. So I can see how if I did these in the wrong order, which I was about to do before, if I did the right axis first and then the Z axis second, I'm still not being that rude. The result would point down instead of up, but I want the Y axis of the camera going upwards. So I will start with the camera direction. This is where this was so funny. Like, you would have seen this in like in-person exams. If you have linear algebra in an in-person exam, you'd look around the exam room and you'd see people going like this. Just go, which way is it? Right? Okay, so camera direction, first one. Second one, right axis. So you can see on the camera, this is going from left to right, which means that the result will go upwards. Yeah. So, is this flipped? Or I hope that the video is not flipped, because, you know, like doing stuff in camera, I can always forget which way this is supposed to be, right? But anyway, I know that the right hand rule is going to give us an up vector if we do the camera cross right axis. And that's going to give us our camera's up axis, which is not the same as the world's up axis. Gotta remember, it's not the same, right? Because the world's up axis doesn't care about which way the camera is aiming, but this one definitely is taking into account where the camera is aiming and its right axis. That gives us an up axis for the camera, which is in one of the dimensions going to end up parallel to the up vector, but not necessarily the others. So we don't need it to be either. So we ended up with a 0, 2, -1. Normalize that, we get our root 5s in again, because this forms a similar triangle in a different position. So what we end up with is a vector which is 0, 2 on root 5, -1 on root 5. Let's go back to our diagram here. Let me just make myself some space here. So I need to make another color. For our camera's up vector. What haven't I used? I haven't used a purple. So our camera's up vector, not our world's up vector, is equal to the direction crossed with the right. And that's going to end up equaling, what was it? 0, 2, -1. I'm just going to use the non-normalized so that I don't just waste all my time in the lecture writing root 5 on everything. And this is going to be this up vector. It's not exactly parallel to the y-axis. It's tipped a little because this camera is above the thing it's looking at. So if it's above the thing it's looking at, it's z. Wait. If it was flat, its y would be here, but since it's looking down at something, its y is tipped forward a little. Okay, so that gives us our 3 coordinates for our camera, and now we have 3 axes for our camera and a position for our camera. So what have we got if we have 3 axes, and we've made sure in the way that we created these things that the axes are orthogonal. So this is a proper axis, so this is a proper coordinate space. Well, I shouldn't necessarily say proper, it's an in-scale coordinate space in a sense, especially if we've normalized it, so it's not skewing any directions or anything like that. What we then have, if we've got 3 axes in a position, is we can now make a transform. So we can make a transform pretty easily by saying, oh, I should have used these colors. I often use like this like combo of red, green, blue, because like when we're doing these other vectors in graphics, we're going to have red as the first one, green as the second, blue as the third. So we remember them that way. But we can take the right vector, which is the x-axis of the camera, and we put that vector in here. Then we can take the camera's up, which is the y-axis of the camera, and we can put that in here. Then we can take the camera's direction, which we said was the z-axis. The z-axis is pointing, for you, pointing out of the camera towards your screen. It's really funny doing this because I'm pointing at the actual camera that I'm streaming on, so it sort of makes entire sense. I point at that camera, and the same vector I'm pointing at you comes out of your screen. So it's nearly like we're doing this in a real world where I have a camera here that you will never be able to see, like by definition of it. So it's kind of like a virtual camera pointed into this world that I'm in here. So it has its own up, X, and Z. I'm trying to make sure that comes out the right way for you. And we put these in here and we get a transform. So this transform is handling any scaling and rotation that is happening in the camera. So this doesn't yet use our position. We're going to need to compose this together with the position. And this might look funny to you. Some of you who have been playing around so far with scale, rotate, and translate matrices would be saying to me, Mark, why are you doing it in this order? Because the order does look weird, right? What we would usually do is scale and rotate something when it's at 0, and then translate it to its position. But if you know the maths of these things, whatever second in this multiplication is going to go first. So what this is actually going to do is going to move something and then scale and rotate. And as we've seen, if you move something away from the origin, then rotate it, it does this big swing around to the origin. Instead of, when you're trying to place something in its position, you would rotate it and scale it and then move it to its position. Then it ends up in the right place. The reason we're doing this is that swing effect of moving things around is actually exactly what we want, because we are not creating a transform that tells us where the camera is. Like, if we want to, we can have like the camera's coordinates and stuff like that to move it around, but this transform is not exactly that. It is not exactly this is where our camera is going to be. This is a transform that we're going to use to put the camera in the center and swing everything around so it ends up having having coordinates that match the cameras. So we're changing things from the world space into the camera's coordinates. So that kind of idea of that swing stuff around effect, we're actually using that now to our advantage to swing the entire world around so it fits the camera's perspective. So that's why this, like, you can actually have, depending on how much you've been playing around with scale, rotate, translate transforms, you can get into the concept that you always want to scale and rotate things before you translate. Here is something that sort of breaks that rule. Like, you're not going to break that rule when you're working with objects, but when you're working with cameras, the world is the object and the camera is the relative to that object. So what we're doing is reversing this because we're swinging the whole world around into the camera's viewpoint. So we multiply these together, and I'm not going to do it with our actual numbers because we don't need to. You can do your matrix multiplication yourself. If you want to, you can go through everything I've done here and spend like a couple of hours on it if you want to, and do all the maths yourself with the cross products and things like that. You should get the same numbers as I did. Cross products and normalization and multiplication. But what you end up getting when you compose these together is a final matrix, which we call the look at matrix. It's a keyword. So GLM look at, I can't remember which one it is, but we can ask OpenGL to actually generate this look at matrix, and then we can use that to then convert the world into the camera's coordinates. Yes, Michael asked something. Is it the same idea that turning my head is the same as the world swinging around me in some sense? Yes, 100% is. So, turning your head could be considered a transform of this object or a transform of the entire object. And that's exactly what the camera is. The camera transform is to say, from my perspective, the way I see things, I see my z-axis here. And then I will change the coordinates of the world based on that. Whereas we could say that 0, 0, 0 is, I don't know, K17. the center of our worlds. But from our camera perspective, our own two eyes, 000 is exactly where you are right now. And the coordinates of K17 don't get to be 000. They get swung around by this composed transform to be some other coordinate. So if I look that way, I know where I am relative to UNSW, kind of. UNSW 000 is off in the distance, but to me, it has a Z value of, oops, just hit my lamp, has a Z value of a few hundred or something like that. I don't know what our units are, right? So that kind of thing. So it's GLM look at that Simon's got there, yeah. So, will we need to do all this math? This is always the funniest question. The answer is no. But if you don't know what it is, you're not really going to know how to use it. So I'm still going to teach you things, even if OpenGL is going to do things for you. So I'm never going to be like, you don't have to. I mean, some things I'm going to say you don't 100% have to understand it. Like, for example, like, I don't always remember off by heart how to do even simple things, like multiply a matrix to a vector, because I've spent so many years assuming that the maths library is going to do it, but I did have to learn it, right? I did have to learn it to understand what was happening. But again, GLMaths library, is going to do this for us, and it actually has a single function that creates this matrix where all we need to do is give it the camera position, what it's looking at, and an up vector. So if you have a world up vector, hang on, that's annoying me. Variable names should not be capitals. I don't know why I had it like that, but yeah. So GLM lookat is a function that's just going to generate this matrix for you. It's going to go through all that maths that we did there, but quicker than we could do it, obviously. But the nice thing is all we need to do is give it these three vectors. So a vector for where the camera is, what it's looking at, and what its up vector is, and it will generate the matrix with which to swing the entire world around so that it is in the camera's perspective. This is the kind of thing that we could call, you know, every frame on a camera that we're moving around in the scene. So as the person walks around the scene, the matrix for the camera looking at things is going to change each frame. We can recalculate this, and then we can then view our scene from the perspective of the wait, Simon said it's not even a typo. Is it actually a capital U in the spec? That would be quite funny. Like, I think I did copy that from somewhere else, and I was looking at it then and just going, why is that a capital U? What's that? Look at camel case. It is in camel case in OpenGL, right? Oh yeah, okay, so OpenGLM does have capitals as some of its variable names. Let's not go into too much detail about the issues that we might find in readability and usability in OpenGL, because that's going to open up a big can of worms that we don't necessarily have time for. Okay, so, but what we're getting at is we now know through all that maths how we would theoretically put a camera together, and we know the reason why. If I say I would like to create a camera matrix, a look at matrix for a camera, saying where the camera is, what it's looking at, and what is the notion of up to that camera, now you know what that means and why it works. So that's where we're at today. So what did we cover today? We looked at how we're transitioning from 2D to 3D. And the good thing is a lot of what we've learned already, it's going to go straight through to 3D. So verts, triangles, textures, transforms, they're all just going to basically be used in 3D. The transforms get a little bit more complicated, but only really rotation. The others are still quite simple to use. But then we also expand the idea that objects are not just going to be flat objects that you can see. We're going to start thinking about objects as having a front and a back. And they're going to be the outside surfaces of things versus the inside surface of things. Definitely more detail on that later. We'll tell you how that's actually implemented later. And then we're also looking at transforms being, this was the big push today really, was transforms being their own coordinate spaces. So objects having their own set of coordinates, and those being different to the world coordinates, but us having a transform that allows us to go back and forth between an object's coordinate space and the world's coordinate space, which also gives us a whole bunch of information about how that object can be placed in the world, where it is, how big it is, what's its angle of rotation, that kind of thing, scale, rotate, translate. So after we've broken those things apart, learned about them, we compose them together and understand that any transform, a single transform for an object, defines a set of 3 axes for that object and their relationship to the identity matrix, which is the world of the X, Y, and Z axes that we're using. Then we put that into practice today by making a camera. So we made those 3 axes for the camera based on the camera's Z axis being vitally important for where it's looking. It's actually where it's looking. Oh no. If that's the camera, it's where it's looking. The Z-axis does not point where the camera's looking. The Z-axis points from where the camera's looking through the camera. So it points out of the screen towards you. I'm just getting confused because I'm just pointing back and forth now, and I'm just confusing myself, right? But the lookout transform is the thing that allows us to then take all the vertices in the scene and swing them all around so that our camera is our camera here is looking at the scene. We swing everything around so the camera is looking directly at the objects in the scene, and that allows us to say that if the camera is looking at these objects, we can put them into a coordinate space that maps to pixels on the screen. So it's vitally important for us to be able to move all the verts around to the camera's perspective. So that's where we're at the moment. What's coming up next is the idea of actually seeing things. So all I've given you so far is a transform to move things around into the camera's perspective. That doesn't necessarily get you visible objects or anything like that. So the idea of the camera's vision and how it might see the world is something we're going to look at on Wednesday. How Chung's just asking that right now. Would we be dealing with perspective later? Yes. We will be dealing with perspective in 2 days, exactly. So 10 a.m. Wednesday, I'm pretty much going to launch straight from this into projections. So orthographic and perspective projections, because now that we have our camera in a position, we know we can move things around. What if we move things around in such a way that looking through and past things makes sense from a 3D perspective? So yeah, we're definitely going to go into it. Yeah. Oh, you're looking at superliminal and how it does weird perspective. Yeah, I'll look into superliminal and see if it's a good example for that. But I may be using more simple examples of that. Jason's asking about frustrums and clipping, etc. Yes. I will try to start talking about that on Wednesday, but I'll see how much I can fit. I haven't written Wednesday's lecture yet. I'm writing them pretty much as like the day before at the moment. I don't know, like it's easier for me to write them the day before because then I don't have to rehearse them because I know I've just written them. But yeah, we'll definitely be talking about things like if you have if you've read on stuff, frustrums, clipping, visibility, culling, things like that. We'll definitely be talking about those. But also not just that, we'll be talking about building up the picture of the world. So this idea of transforms being like inseparable from objects, like every object has a transform. We're going to be looking at transforms relative to each other. So the entire scene that we're looking at is actually a hierarchical tree of transforms. Again, I'll talk about it in detail. It's not something that I'm just going to say and then just leave. So I'll tell you how that stuff works when we get to it. Okay. I'm going to wrap up the lecture there. Thank you all for coming along. I will be back in a couple of minutes' time and answer any questions people have. If you want me to go over the maths or the diagram again and stuff like that and show you how we actually did all this, yeah, I'll stick around for a bit and answer anyone's questions. All right, I'm back. Um, oh, thank you for the people who are saying thank you. Um, do we have any questions? Does anyone have anything they wanted to go over or they want me to poke more at or anything like that? Nix is asking, is there somewhere I can ask questions? I am a bit stuck on one aspect of shaders, not sure where to ask. So, two definite points of call for the course. First one being the Ed forum. Let me just... There's the course forum on Ed, so basically, like, official content questions there. Course forum's a very good place to ask them. The other thing you could do is ask on the course Discord. Course Discord's less useful for that stuff because it just depends on who's there at the time, and questions tend to get pushed back through. Course Discord's more for chatter, for us to just sort of talk about things and stuff. The course forum's the best place for that. So if you're in WebCMS, you've got to make sure you're logged in to be able to see it. You can see these are student limited, so I'm not making these publicly available. Anything that we're doing as a service as part of the course is something that like only students get access to, but the lectures and stuff are public because I just like the idea of being open about stuff like that. But yeah, I think potentially if you're asking about one aspect of shaders and stuff, the Ed's a good place to ask, and you can also ping the Discord if you want to. There might be another student there at that time who could give you some answers right away. David saying I should watch Passion of the Craft to keep updated with Minecraft. I haven't watched much in terms of YouTube for Minecraft or anything. Also, I only have so much time in my life for the number of games that I'm trying to play. I have like a group of friends that I will often play things with. We've played a bit of Aliens Fireteam Elite recently. I've got another group of friends where we're replaying through Borderlands 2 again. And every now and then people I play Genshin with as well, so it's kind of like I have so little time to actually get stuck into different games, especially because Minecraft is such a time sink game. You can sink so many days into that game if you really want to. And part of me wants to, but again, I kind of like I'm too busy. Kind of it's like I'm so social with my gaming in a sense. There's very few games that I play on my own, so Minecraft feels like one that I would initially play a lot on my own before joining up with other people. So I don't know if I have the time to fully get into it, but maybe just watching some videos on it's good. Does OpenGL let us nicely tie a camera to our mouse input? Sort of. You can use keyboard and mouse input to drive transforms, in a sense. When you think about it, if GLM is going to do this, then what we can do is we can take the current position of the player or the camera in the world and the target. And the target might be the only thing that's important. We can move that target around using our mouse. So we can do stuff like that. Yeah. I'm paraphrasing the way it works, but basically this target vector you can rotate based on the X and Y coordinates of your mouse at any point in time, or even more importantly, the delta of the mouse. How much has the mouse shifted from its previous position in the last frame over a certain amount of time, and you can change your look at like that. So it's not super hard to do. Andrew's asking, don't worry if it's a lame question, Andrew, it's probably going to be fine. Still trying to set up Tute 1 and can't get it to compile. Windows VS Code. Say the best way for you to progress. Help session is when the assignment is due. Yeah. I think that you probably want to get in touch with your tutor and talk to them about it, and so you can get some of that going this week. Also, look on Ed because a lot of people have had little issues with it. And so it might be something really, really simple. So a lot of the configuration stuff might just be simple things that will get you going. Passion of the Craft is a horror short by Meat Canyon lol. Oh, is this like, was that a troll? Was that trying to get me to watch something that was going to like scare the crap out of me? It would have worked as well. You would have gotten away with it too if it weren't for those pesky kids. Chicken's back. Jason's asking, can you talk a bit about the performance aspects with camera transforms, since we're applying the matrix multiplication to each vertex for the camera space? Yeah, I mean, like, applying a matrix to each vert is actually not super expensive. So the trick behind this, yes, we do have to apply a matrix to each vert, but we simply can't see things unless we apply some transform to each vert, so we still have to do it. The trick is that we build this transform up entirely, so we put a whole lot of effort into building up the transform until it is complete. And that way, what we're doing is we're doing a lot of edits on one transform, which is not expensive. And once we're down to a single transform, that transform gets applied to all the verts. So it's the kind of thing where we can make it reasonably cheap, because matrix multiplication to vertices, so this floating point calculation thing, is exactly what the graphics card is very, very good at. So applying a matrix to a vert is not super expensive on the graphics card, and as long as we're only applying one matrix to each vert, you're sort of okay. And so what we do is we compose all these matrices together till there's only one matrix, and then it goes and hits all the verts. So it's not necessarily a performance hit, but it's like an order n, in a sense. Like you're going to have to do something for every vert, but you're always going to have to do something for every vert. Even if nothing else, you are going to have to access all the verts to pull color and texture data from them. More than color and texture when we get down to it. You're applying lighting as well and stuff like that. So if we're going to be working on every vert individually, each frame, then we can transform it while we're doing it. So it's not super, I wouldn't consider it one of the things that we watch out for with performance hits. You can get a much, much worse performance hit by using models that are too complicated. So we get this thing where, like a lot of people nowadays are doing this thing called photogrammetry, where they take a whole lot of photos of an object, and based on all of those photos and mapping sections that match each other color-wise, you can build a 3D object out of it. I actually did it with some of the miniatures that I painted years and years ago, and it was really, really good. But every single curve was covered in verts. And there were so many triangles in it. And just the sheer number of verts and triangles is a thing that definitely causes performance issues, because those kinds of things are like, so much stuff we're doing is order n on the number of verts, or it's order n on the number of pixels, depending, and other things like that. Or we're multiplying the number of verts by the number of lights that we have in our scene, those kinds of things. So the number of verts is often something. So heaps and heaps of games, like I've showed an example like Borderlands 3, you can see other games that perform remarkably well for how good they look. And often they will have just a really low number of triangles, but be using some other trick to make things look good, or using a particular artistic style that doesn't require a lot of triangles. I remember World of Warcraft is a really good example of this. Very, very exquisite hand-painted textures, super low polygon count. So their idea was their design aesthetic was not realism, so they didn't have to make things real, so they make things blocky instead. And what they did was they opted for a large amount of human preparation time and a low amount of rendering time, so that this game would end up being more accessible on lower spec platforms. And it worked for them for many years. They had a massive player base for many years because it was so easy to play the game. So that kind of feel. So I wouldn't say that performance of the camera is something that we're too worried about, and because we're hitting every vert anyway. So if we're hitting every vert and multiplying something, we know that we're already pulling that vert out of memory to process it. So that's the big cost, is the fact that we have to load every vert from memory and do something with it. If we do a little bit more with a bit of maths, not too bad. Yeah. So hopefully that answers your question. That may have gone further than your question was expecting, but I think these are interesting questions anyway. Okay, that was Jason's question. Nick's Avanel is saying, generally I'm just not sure how to send in values for colors into the shader, since what we've done in the tutes have either been textures or hard-coded colors. Are you talking about colors from vertices? Because you know how you're sampling colors from a texture. You can sample a color from a vert if the vert has a color. So not all verts have colors. You know how we started off with like just like the vert, not the vert shade, the frag shader is just going to override any color information. Just say the whole image is this, the whole object is this color. You can take the color from the verts, so you can have your verts have a color as one of their attributes. You'd have to set that up as one of their attributes. You'd pull from that attribute and set it as an output of the vertex shader, and then make sure that the fragment shader takes that same value as input, and then you can linearly interpolate between the colors on different vertices. So I think we showed that actually with a like that rainbow looking rectangle and stuff like that. If you look at that, you'll see the code in the shaders that's going to pass those values through. You just got to make sure that if anything's going to be in a shader that you're pulling from vertices, then the vertex attribute has to exist. So it has to like exist in a layout and has to be like, go, this is, you know how we were talking about how we set up the memory for the vertex. So the first three floats is going to be the XYZ position. The next three floats, if you want to, can be RGB. No, they're going to be in fours, you know, XYZW and RGBA. You would grab those values from that, and then you could pass that into the fragment shader and it would use those. So if you're looking to grab colors, you can have vertex color information, and you can sample that by grabbing it from the vertex shader, passing it to the fragment shader, and having the fragment shader interpolate between those colors. We do have some examples for those if you want to look at them. Logan's asking, can we turn a 2D object into 3D during runtime in OpenGL, like what we do when we're modeling in CAD software? Yeah, maybe. When we say in real time, then we are asking about whether we can do this in a performative way that's actually going to work. So if you have a 2D object and you want to create extra geometry in it, so you had the idea of all these verts and you wanted some of it to like emboss, to like pop out of it, you can do that kind of stuff. There is actually a geometry shader that can do things. You can even do it without a geometry shader. You can do it with a vertex shader. So for example, we do this a lot when we're stuffing around with maps in games. So we have a flat 2D plane, but the flat 2D plane is not just a rectangle. It's not just the verts on the corners. Let me draw this. New. I don't know if I should save that or not. No, I won't bother. It's like a whiteboard. Okay, so flat 2D plane. It would have way more of these than this. Put like thousands of verts in this. This is like procedural generation. So we can do procgen. That's the weird shorten it. I'm not going to stop saying stuff like that. It's procedurally generated terrain height maps. So what we can do is we can use maths to grab all of these vertices, all of these individual verts, like here, here, and here, and in the vertex shader change their positions. So this one can go up. This one can go down. This one can go up a little bit, that kind of thing. And you can use like noise generating algorithms to do this. So Perlin noise is the one that we would use a lot. Perlin. So you can do a Perlin noise height map on this thing, and then what it will do is it will go across this surface and make it kind of like smooth ups and downs on it. So you can do that really in a vertex shader by just changing the y coordinate of all these verts. And so your in position, out position are not the same. You change the out position by moving things up and down. The next thing that you can do that's really cool is I can have 3 textures. So let's just make 3 two-dimensional textures. And I'm gonna cheese this, right? Because I'm not gonna do this properly. So what I do is, based on the y coordinate of each of these verts, I sample from a different texture. So the ones that sink down get this blue texture because they're water. The ones at the medium level get this green texture because they're grass. And the ones that go high up get this gray texture because they're rocks. And then that way you get like this, you can create a map that looks good from a distance. It won't look good up close because you're stretching these verts up and down, which means some of these triangles are just getting incredibly long and their texture coordinates get all messed up and stuff. But from a distance, this will look okay. You'll get away with this and it'll look like, ooh, there's rocky mountains over here. And over here, there's a river that flows along this distance, because depending on how good your noise generation stuff is, you can get that kind of thing going. So you can have this kind of like big 2D map of verts, and a mathematical formula like Perlin noise that just shifts them up and down by certain amounts. And then you have thresholds for different heights, like the sea level will be a certain height and the tree line will be at a certain height, and that's how you swap between those textures. And then you can build your kind of like low level distance view of a two-dimensional land, in a sense. And so you can do that for off in the distance when you don't care what it is. Or if you're going to do it manually, you won't use the randomized thing. You will actually draw rivers and things like this. And then you go, okay, this is the map of the world. You put that in, but you can still have the idea of different heights end up with different textures and things. So that's one thing that you could do if you wanted to. Where was that question? Of like turning a 2D object into 3D. You kind of can. It only works in specific cases. There's plenty of ways where you can go. You try to do that, but there's just simply not enough information to make it work. But this is one example that we definitely do, that we can generate this. And Minecraft does this kind of thing where, like, it doesn't do it in real time, but it'll generate a whole world like this. It won't, I don't know what algorithms they use to do it, but I know that they get, reasonable looking, natural. I mean, it's made of cubes. I can't call it natural, but natural environments. And you'll get this same kind of thing where, depending on the height from the sea level or the zero level, they will have different properties. So the deeper you go, the more likelihood that it's going to be minerals and stuff like that. The higher you go, the less grass there is on things, and the more it's rocks. And they have some other algorithms to plant trees at certain places, but different trees will be at different altitudes and stuff like that. So they may use the same kind of thing where the altitude map, the height map, might be built via a noise generator, and then other algorithms will come in and say, depending on the height map or the proximity to water or other things, or whether there are cubes above or below these things, they will generate different criteria categories for things that should be there. So that's people are asking questions today that are sending me off on interesting tangents, but I think that's kind of fun. So Logan, I don't know if that answers your question or not, but that's a big answer to your question about like trying to turn a 2D object into 3D during runtime. There are other things that we can do, which is the geometry shader and tessellation and things, which we might have a look at some point, which is the idea of adding vertices to objects. But often when you're adding vertices to objects, the thing that you're doing is taking a jagged edge and smoothing it by adding extra verts in places where it's jagged. But that's not necessarily making something 3D, but you can use those shaders definitely to add 3D information to a 2D object. Conrad's saying you've done some photogrammetry captures. Yeah, they're interesting, right? Because like you get some really, really cool looking stuff in 3D, but if you drop them into a 3D world, they tend to suck up a lot of your rendering resources. Because I did a miniature, it's like a 4 centimeter tall miniature, and it had like 100,000 verts. And I was like, no. Took it to a friend of mine who's a game artist, and he was like, yeah, you want to be careful with that. Like, yes, it'll work, but we would probably import that thing into something like ZBrush, smooth it out, take a whole lot of the triangles out of it, and just lower the poly count of it, the poly count being the number of polygons in it, and then you might be able to use that in a real-time application. Oh, Simon was wanting to say something about row versus column major order. Otherwise, we can talk about the tutes. Oh, like depending on how OpenGL is doing your matrices, whether they're in um, an array of columns or an array of rows or an array of columns. Yeah. Um, we may have to take that to the tutes. I reckon, like, if we do want to talk about that, like, now is already a little bit too late in the lecture. This is, like, now optional content. So let's put it in the tutes so that people know exactly how we're working with that stuff. And Jenny's helping out also with Nick's there about, like, yeah, the OpenGL starter code that we showed you stuff about sampling colors and stuff. So hopefully that helps. How Chung saying Final Fantasy VII could be a good game to start another lecture. It totally could, except I don't have the old version running anywhere. I don't have the new one either because I don't have a PlayStation. But the old version is really good because it's an example of super early polygon rendering. Like the number of polys is like so low there. Yeah, and Conrad's saying some software lets you decimate a mesh and then reproject textures onto it. Yeah, so you could do something like with this height map here. Anything like this one here that's lifted really high, you would add extra verts along the height of it, and extra textures. So you'd have a different texture for like cliff sides, not just this texture that's flat onto the top and then stretched. Because this kind of thing where if this gray texture was the same size as the entire rectangle, the green one's also the size of the rectangle, and the blue one, if you're not doing repeat or like what we would do for these usually is like mirrored repeat textures. Either way, the vertex texture coordinates would be kind of fixed to that pattern. And the more you stretch things vertically, the more the texture just goes, yeah, it turns into this long stretched out thing. So you'd have other textures for things like that. It gets to a certain point with these things where you don't really use them. Like you use them for distance, but once you got close enough to see the cliff, you'd want to have actually modeled that. And there are systems for doing that, for modeling like kind of like rock features, terrain features, either out of pre-made bits and pieces that you copy paste multiple times, or on like procedural generation in a different way than this kind of height map that I've got here. Jason's asking, what kind of situations are 3D textures useful for? So 3D textures are useful for using up all your graphics card memory. I kid, I am joking, but they will do that. One example that I was using last time was the idea of probably the same kind of noise generated three-dimensional wood grain texture, so that when you create an object that is as if it was carved from that wood, it picks up the texture information from 3D information inside that block of wood, and so the wood grain is really clear through it. So you can see how the wood grain would go through the object and have its sort of cuts through and stuff like that. You can do the same thing for marble, so that the grain of marble goes like realistically through a pillar or something like that. The funny thing about both of those is that the cost of storing the three-dimensional texture means that in practice no one does it. But it's still possible. It can still make sense. You can also use things like this one here could be a three-dimensional texture, where instead of having one texture for grass, one texture for water, one texture for rocks, you have a 3D texture that fades in between these things. So between the green and the gray is going to be like some brown bits and stuff. So like the bare soil in between the tree line and the kind of the rocky area of a mountain above it. And we can have smatterings of snow on this, and as it gets higher you get more density of snow, and a 3D texture would allow you to have that kind of fine grain on the different levels. Again, it's just gonna burn so much graphics memory. So it's rarely used, but you can see different ways that it could work. You could try doing something like a 3D texture for the water as well. So if this was in a distance and you didn't require things to be moving, you could put things like schools of fish in there, and if you sample it, then you can see these fish kind of appearing and stuff. But again, it'd be so much cheaper to make the fish as their own objects with verts and triangles and just put them in than it would be to have so much 3D texture information. So there are examples of like the use of 3D textures like that kind of thing, but it's rare. It's rare that in a performance situation we would use it, because the amount of memory it takes up, and because a lot of the time what we want to do is we want to minimize the burden on the graphics card, and instead we will like maximize burden on artists instead. So you take any AAA game, those big games like your Grand Theft Autos and stuff like that, the artists are working for like 6 months and then the programmers appear. You know, like if they're doing it on contract basis, the programmers won't even appear in the studio until midway through. So the artists will be working for months just like concept arting and then like building up textures, building up models for things and stuff like that. We don't even need them to work yet. You know, we're just building up all of this kind of art assets, and it takes relatively less work for the programmers to get those art assets going. But it depends. Very much depends on the company. Some people go programmers first. So the programmers build this monstrously powerful engine that can do amazing things. Looking at like Crytek back in the day when they're making the CryEngine 3 and stuff like that. And then they go, okay, we need a game to show this off because otherwise we're not going to be able to pay for it. So it's like Crysis is like, it's like a medium good game. You know, it's like, it's reasonably exciting. Some of us played it through to the end and finished it. And it was like, okay, that's cool. But what it was there for was just like, hey, look at that shadow. See the shadow of like that telegraph pole? It's like distinct and has hard edges, and the further it gets out, the more feathery it is. It's like someone went through and just made the graphics engine capable of feathering the edges on those shadows as they got further away from the thing that was casting them, which is a real property of light. But one that we don't often see always working in games, and that was the point where that kind of thing appeared. They also worked on stuff like tessellation, so like when you're far away from an object, it has less verts. And so one of the things was like rubble. So the rubble was just like a rectangle with a texture of rocks on it. But as you got closer, the rocks would actually kind of like, I don't know if you could see it if you walked up to it at a really specific angle, you could see the geometry grow out of the texture as you got closer. And so it would be like these verts were actually appearing in the texture and they were mapped to like certain parts of it. And then it would have lighting as if it had objects in it and stuff. And it actually would end up with three-dimensional stuff. So I think those were two of the things that the CryEngine 3 did first, which I think was that kind of shadow tech and the tessellation. Also, destructible objects. The ability to take something that could have been 4 verts and stuff, like, what's the Division or Rainbow Six Siege? I can't remember which one. The Tom Clancy games, the current ones. You blow a hole in that thing, and then suddenly it has all these extra verts that it didn't have before. So, systems to build that kind of stuff, also very, very interesting. Anyway, you have allowed me to go on these fun tangents. These tangents are fun, and this is kind of like why we study graphics, because there's so much cool stuff that people do. Now that I've shown you the basics of, you know, just texture mapping and stuff like this, you could see that, like, well, each vert has an XYZ coordinate. We can move the X, Y, and Z, and then we could put stuff in the fragment shader that says, depending on the Y value that we're getting from the vert, we would actually sample from a different texture, you know, and that's super cool being able to do that, right? Smudged pasta. Hello, sir, of this class in which I attend. What game were you playing before class? What was I doing? Before class today, I was looking at the new Genshin event. So a new event just started today, and I was playing that. Last night, while I was making lecture slides, I was playing World War Z Aftermath, which is a new kind of co-op horde zombie shooter that got got refreshed. It's not like it technically came out a couple of days ago, but it's not new. It's like a major update to a previous version of the game. And it's okay. Neither of those games are going to be breaking any ground significantly in a graphics sense. So, happy to talk about them, but like, it's not a huge amount going on. Sam was playing Valorant yesterday. Yeah. And when you hit something with a knife, it plasters a texture on top of a surface. So that's what bullet decals are. Decals are a thing in graphics where you take a rectangle and you put it on an object, basically. So bullet holes in games are usually just a 2D texture that's slapped on an object roughly in the position that you shot it. Every now and then they'll do small deformations in it, but usually those deformations will not be geometrical because they won't add vertices, but they will fiddle with the normals. And I am not going to explain that yet because I am going to spend plenty of time explaining what the idea of fiddling with the normals means. Yeah, I'm not going to talk about it. But yeah, they will do that kind of thing to make it look like stuff's been hit. Yeah. So there's heaps of... Oh, Smudge Passer said the stream thumbnail exposed my gamer side. Yeah. I was actually tricking everyone because everyone expected me to play Quake at the start of the lecture today, and instead I decided to reference The Matrix and risk a copyright strike. So we'll see if the first minute or two of the lecture gets cut out of YouTube after I save it. So we'll see how we go. All right, I'm going to wrap it up there. Thank you all for coming along, and hope you learned something with the extreme maths that we were doing today to get cameras working, and also some of the other sort of implications of what we know. The more we know, the more I can show you sort of interesting, strange things that can be useful and stuff. All right, thank you all. I will see you on Wednesday. Wednesday, we're going to get closer to these cameras actually working. I don't want to say working like human eyes, because they don't work anything like human eyes, but closer to. Like, we're going to add a few more things for believability and realism of vision. Okay, see you later.